So yeah, in the last lecture we looked at the shortest path problem from one node, and we looked at an like a greedy algorithm for it, and we showed how to do that in order m log n time. Right. Now in this lecture we are going to look at another graph problem, which is called minimum spanning tree. So what do we want? We want that, okay, we are given a graph. Suppose the graph is connected. So we want to preserve the connectivity between all the nodes. So we want a connected subgraph. Okay. But we want to connect them as cheaply as possible. Okay. So let's assume positive costs for edges. Let's denote them by CE. Okay. And what we want? Connect all pairs of nodes as cheaply as possible. Given the graph is connected, of course. Sorry. So here maybe now you don't want to use all the edges of the graph, and you want to find a subset such that all the nodes are connected to each other. And since this is, you want to do it as cheaply as possible, this graph will turn out to be a tree. Why? Because if you have a cycle, then you can always get rid of one edge since all the edge weights are positive. So after getting rid of one edge, whatever you get is going to be cheaper than what you had earlier. Okay, so that's why this graph is going to be a tree always. Good. So let's just like formally say it, that what is the input for the problem? Input for the problem is a connected graph G and let's say some cost CE for all E in A. Right. And what is the task? To find, so let's like say that we want to find a subset of edges, and that's what we'll call a tree. Okay. So T subset of E such that G prime is equal to, let's say, V comma T is connected, and for which this quantity is minimum. Okay. So this is what we want, that we want the graph to be connected. The graph induced by the edges in T has to be connected, and we want the cost to be as small as possible. Okay. Any questions about the definition of the problem?
The graph is undirected, right?
Yes. Here the graph is undirected. Okay. Any other question? So first lemma, as I said, very simple, is you can just show that the graph G prime is a tree. And proof is easy, I'm not going to do that. Okay. So now this tree, or T subset of E, is called a spanning tree.
So in the input, we should be mentioning that C is positive, right?
Yes. Yeah. Positive C is. Thanks. So T subset of E is called a spanning tree if V comma T is connected. Okay. and that's why the name minimum spanning tree. Okay. So now the question is that, okay, how do we find this minimum spanning tree, minimum weight spanning tree, minimum cost spanning tree? Because how many spanning trees can be possible? So suppose you have a click, if you have like, all the edges there, then there are a lot of spanning trees possible, right? So generally it's like exponential number. Okay. So how do you then select one out of this? How do you find the minimum weight spanning tree? So the possibilities are endless, but still, how do you find the minimum weight? And there are, a few algorithms known which all of them like produce the uh, minimum spanning tree and which look like quite different. So we are going to like first list down the algorithms and see how they work, as in what they do, and then we'll see that, okay, what is the commonality between the algorithms and like why they work uh, in producing the minimum weight spanning tree. Okay. So even though this is exponential number, generally still we can like find MST in polynomial time. How? Using the algorithms below. Let's look at the algorithms one by one. So algorithm one is called Kruskal's algorithm. So again, you might have seen this in the data structure and algorithms course. So what does it say? That just find the minimum weight edge in E. So find the minimum weight edge in E that is not already added. Okay. If the edge creates cycle in, in whatever has been added, then we throw the edge away. And keep doing this till span all, we span all the vertices. And what we mean by span, that every vertex can be reached from any other vertex. So whenever an edge is being added, like, yeah, you can just see that, okay, whether all the vertices have been added or not. Or you can just do it for basically n minus 1 times. That is also good. So this is one algorithm. So what does it do? The first algorithm, it just adds, looks at the minimum weight edge in the graph, tries to add it to the tree. If it remains a tree, good. Go for the next edge. If it does not remain remain a tree, then like again find the cheapest edge and add that. Okay. So is Kruskal's algorithm clear? I mean, you must have seen it, but I mean, yeah. Even now, if there is some doubt about how the algorithm works, please tell. Okay. If not, then let's go ahead. So the second algorithm is Prim's algorithm. Here, instead of adding the edges arbitrarily from the graph, like now we have some direction. So what does it say? Start with the node S. Okay. Keep this. Okay. Initially, you initialize a set S with just small s in it initially. Now find a node V which is not in S. Okay. That can be most cheaply connected to S. That is minimizes what quantity? Minimum of U belonging to S, cost of UV, right? And then add UV to T and continue till again for let's say n minus 1 steps so that all the vertices are reached. Okay. So here instead of suppose you have some graph. Suppose this is your graph one. So now suppose you start from Kruskal's, then Kruskal's will first add edge, this edge, then it will add this edge, then it will add this edge, then it will add this edge, then it will add, okay, so I didn't put any value on this, so let's call it whatever. These two I have not put anything, so let's call it 20 and let's call it 15. Okay. So now,
Sir,
of
are you
course,
performing Kruskals or Prims?
I'm performing Kruskal's right now.
Sir, but
No,
you added
no,
4
no, no. I'm
after
performing
5.
Prims. Yeah, because after Y5 got added first, I started with this node. So okay, so let me go back a bit. So I wanted to perform Kruskal's, but in the middle I changed. Yeah, so let's do Kruskal's. Sorry. So first 1, 2, 3 get added. So I'm performing Kruskal's right now. So first 1 gets added, that is the cheapest. Then 2 gets added, that is the cheapest. 3 gets added, that is the cheapest. Now this 4 will get added. Then this 5 will get added because that is the cheapest and still not causing any cycle. Okay, and then I had put let's say 15 and 20, right? Then this 7 gets added, still no cycle. Sorry, 6 gets added, and then 7 gets added, still no cycle. And then if you add this 10, then there is a cycle. So you will not add this 10, and instead you will add this 15. Okay. So this became uh, like a run of Kruskal's algorithm. Suppose we now start Prim's algorithm. Let's start from this S. Okay, some random. So now what is the cheapest way to add something? Cheapest way to add something is this. Is this. Yeah. Is there a question? Sorry.
No, sir. No, sir. I was just answering 3.
You were. Yeah. So for this S, 3 is the cheapest edge to be added. Then the next cheapest edge will be 2. Okay. Now the next cheapest will be 1. to add. The next cheapest will be 5 to add. Next cheapest will be this 4 to add. Next cheapest. Now, if this 10 is added, then this is within S, within this capital S, because capital S now includes this node and this node. So this 10 will not be added again here. Instead, this 15 will be added, this 7 will be added, and this 6 will be added. So as you see, and as you might have seen earlier also, that these two algorithms, even though start very differently and traverse the edges very differently, they both produce the minimum spanning tree. Okay, and there is a reason like why I took for now that all the edge weights are distinct. So we'll assume that for now. Okay, there is another algorithm actually, which we will not be doing in that much detail, as we'll be doing Prims and Kruskals, but let's still mention it. It's called reverse delete. It's like sort of opposite of what Prims does. So what does this algorithm do? They just like throw away the highest weight edge in the graph if the remaining graph is connected. Okay. Again, keep doing this till left with a tree and -1 edges, right? So this is like, what was Prims doing? Prims was adding edges, the cheapest edges, such that you reach a tree, so that you maintain a tree. This one is removing the highest weight edges till you are left with a tree, right? So let's also look at its run on this graph that I just made. So it throws away this edge. Throws away this edge first, because this is 20, this is the highest, and removing this does not make the graph disconnected. Then it tries to throw and to throw away 10, it can throw away 10. Again, you get the same spanning tree, minimum spanning tree. Okay. Any questions about this algorithm? Okay, so what makes these algorithms, perform the same task? So how do all these seemingly like unrelated or different algorithms produce the minimum spanning tree? So the answer actually is, for Prims and Kruskals, the answer is the same, that there is some property that they exploit, and for the reverse delete also it's kind of similar, but I mean from the opposite direction. But let's see what kind of property this is. So let's do the proof of correctness for the algorithms. Okay. So for that, we want to show a lemma first, which is going to be central in proving the correctness. Okay. So again, assume all edge weights are distinct. and let S be a non-empty strict subset of V, okay, and let E is equal to VW be the cheapest edge with one endpoint in S and other in V minus S. Okay. Then E is part of every minimum spanning tree. Of G. Okay. So this is the lemma that we want to show. Is the lemma statement clear? So what we want to show that we look at an edge that is the cheapest between two parts of the graph. So we have these two parts. This is S, this is V minus S. And if E is the cheapest edge, so let's say E as we called it was VW, then and if E is the cheapest among all the edges that go across from here to here, from S to V minus S, then we say that this E is part of every minimum spanning tree of G. Okay. So that is going to be basically our rule, or that okay, if such an E exists, then we can add it, without if we can identify such an E, then we can add it without worrying too much, because this is going to be part of every minimum spanning tree of G. And we'll come to how this will imply the correctness and so on. But is the lemma statement clear?
Yes, sir.
Okay, good. So now, any ideas about the proof?
Oh, sir, we can say that there will be only one edge between S and V minus S.
In the tree, right?
Yes, sir.
Yeah,
Yes,
but
in the tree, in the MST, there will be only one edge between these two subgraphs.
why that is the true? That
Sir,
might not be
because
true.
in the MST, S will be connected
Let me
and
just
V
show you.
minus.
Let me just show you a counterexample, and then you can speak if I'm wrong. Okay. So suppose the MST just looks like this, and this is your S, and this is your V minus S. Suppose your graph itself is this.
Oh, yeah, sorry.
Yeah.
I didn't think of
So
that.
just need to be slightly more careful. Yeah. Any other ideas?
So there
Can you?
has to be minimum one edge between them,
There must
and
be minimum one edge between them.
to connect them,
Apart from E, you are saying, or E is there?
uh, including everything between S and V
So then
minus
E
S,
is
there
there
has to
anyway.
be at least one.
But that edge is there E anyway. Or let's say E is, yeah. So if E is the cheapest one, then we are fine if E is the only one. So the proof is going to be contradiction, okay? That suppose there is, suppose E is not there, E does not belong to the minimum spanning tree, where T is minimum spanning tree of G. Okay, so suppose E does not belong. So that means now, so kind of what Sean was saying, that in now T, there has to be some edge which goes from S to V minus S. And if that is not E, then there has to be something else. Because otherwise the graph will not be connected, right? In fact, there should be a path from V to W that goes across. So there is a path. So okay, let's first do that. Okay, interesting. So there has to be an edge E prime that goes across S and V minus S. Okay, so there is this E prime. Okay, so let's say this is V prime, W prime. Now the idea is that we want to have an exchange argument. What we want to do, we want to do T minus E prime union E, and we want to show that this is a spanning tree of minimum or of less weight than T. So let's call it T prime. So this is what we want to show. We want to do this exchange argument. We want to remove E prime from the tree and we want to add E back. So this is very clear that cost of T prime is less than cost of T. Why? Because we have removed a higher weight edge, which is E prime, and added a lower weight edge because all the edge weights are distinct, right? So this is fine. So now all we need to show is that T prime is connected. The T prime is a spanning tree.
Sir, have you assumed that there is only one edge going from S to V minus S,
No, 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 no.
which is E prime for now?
No, no, no. I just looked at any edge which goes from S to V minus S. There can be many edges. I looked at
Okay.
any, but all of their costs are going to be more than E because E is the minimum weight edge between S and V minus S.
Sir, we can say
So
that
this
E
need not be
and
connected, right? Like if I
Yeah,
remove E prime and add E, then it need not be connected, right?
exactly.
yeah, sir. So we can
So
say
so
that
like
E and
we
E
can
prime are
choose,
in the same cycle.
yeah.
Yeah, I mean, so good. So this is what I was going to come to, that if we do it this naively, then we might not get, because what can happen, as I actually had removed the example, but in that example also this was true, that you have this. So E is suppose the like cheapest edge, and you have something like this, let's say, and you have this, and then you have this and this, right? So now E is in the, sorry, E prime is the minimum spanning tree. But if you remove E prime, then you don't get, like, the graph is not connected, right? So how should we choose the E prime? Yeah, now Manish, you were saying something about how, so this does not work definitely.
Yes, sir. I wanted to say that if when we select E prime, we have to choose an E prime such that E and E prime are in the same cycle. Because if we don't, then adding E won't connect the graph. So, for example, if initially we had the choice of E, and then instead of E we are choosing an E prime has to connect the whole tree, and so E prime,
Exactly.
adding E prime should connect S to W.
Exactly. So it should connect S to W. Yes, that is the point. So let's, for choosing such E prime, and we also have to maintain that, in this tree, because we are not perturbing this tree too much. We are just removing, sorry, this tree T. We are just removing one edge and adding another edge. That is all the. So what we can, what we know definitely, that there is a path from V to W in T, right? Let's say just path for now, because P I'll use later for the proof. path between V and W in T, just in the tree, and the path does not include this edge E, right? That path is in the tree and E is not in tree. E does not belong to T, right? So that means there has to be some path. So let me remove these. So there is some path. It goes somewhere here. Then it comes to some vertex. Then it comes to some vertex. So that path has to leave S and come to V minus S at some point. So let the last vertex in S be V prime and the first vertex in V minus S be W prime. Okay, so let's look at here. So let's call it V prime and let's call it W prime. Again, the path can go somewhere and reach W. Okay. So now we want to perform this operation with this E prime. Again, we look at T minus E prime union E. Okay. And now again, we want to claim that this graph is connected. T minus E prime union E is connected. So how can we say that? Okay, so let me just, to make it slightly easier, let me call these tree edges. Okay, and now what I'm saying is that remove this and add this. I mean, there might be other things in the tree.
Removing an edge from a cycle does not affect connectivity.
Sorry?
Removing an edge from a cycle does not affect connectivity.
That's not, that is correct, but the whole cycle was not present in the tree anyway.
So like if we add E, there would be a cycle, right?
If we add E, there will be a cycle. Yes, that is the point. Okay, so I thought like removing from the tree will not affect connectivity, but yes, so that is correct. So look at T union E. Okay, it has a cycle, and now what do? That remove one edge from this cycle, and as Shravan said, removing an edge from the cycle does not affect connectivity. We have that T prime is connected, or T prime spans V, or V comma T prime is connected. And we have already shown that the cost of, let's say, C of T prime is strictly less than C of T. So which is a contradiction to T being MST. So just to repeat what Shravan said that, okay, we add this edge now first to this T. Now this T contains a cycle because all these edges are in T. I mean T union E, right? Now if you remove just one edge from this, from any cycle actually, then whatever you could reach from any vertex to any other vertex, you could reach it from the other side. Okay? So even if there was a path, which was using this edge, whenever there was a path like this, you can just go around and do that. So only the paths which use this edge can be affected in the graph. So I'm just making it slightly more formal. So saying that removing an edge from a cycle does not affect connectivity is like very correct. But if you want to make it more formal, what does it mean that it does not affect connectivity? That if there is a path from some x to y, okay, in T, then we want that path to exist in T prime also. So the only way that path does not exist in T prime can be that the path uses this edge E prime. Okay, so it goes to this vertex V prime and then uses the W prime, then goes to W prime. So instead of what we'll do in the path, in that path we'll come to V prime. Then instead of going, okay, sorry, V prime was here. We first come to V prime and instead of taking the edge E prime, we take the other side of the edges of the cycle and reach W prime and then continue just as we did on that path. So that path had U prime, V prime, and before it had something, after it had something. The before and after things are still there in T prime. It's only that this edge went missing and this edge you replaced by this long path. So still there, the connectivity is preserved. Okay, so just like making it slightly more formal so that you get used to the formal arguments. Okay, any questions about the proof? Okay, so in this lemma, we showed that if we look at any S and V minus S such that, these both are not empty, then if we look at the minimum weight edge, which goes across S and V minus S, then that edge has to be in every minimum spanning tree, right? So now let's just use this to show the correctness of Prim's and Kruskal's. So let's actually first do let's first do Prim's, right? Because Prim's definition itself is exactly that. So what does Prim's do? Prim starts with a vertex S and keeps adding, keeps finding cheapest V to add to S. That is minimum of, so V in V minus S, right? So it finds minimum over all E is equal to UV such that U is in S and cost of E, right? That is what it finds. And this by definition is that if you have an S and then you have this G minus S, okay, not this one actually, but fine. This one is slightly more involved, but ठीक है, करते हैं. So so now you have this S and G minus S, and by definition you are looking at some edge that is between S and G minus S, right? Actually, this one is not more involved. This one is the easier one. So you get that edge E that is of the form UV. Okay, so clearly this edge is between S and V minus S by definition, and this is the cheapest edge by definition of this thing, because this is the only time we encounter this S and this G minus S and we find the cheapest edge. It's not that some cheaper edge can be selected, because this S can be encountered only once in the algorithm, and hence this uniquely determines the edge, and that edge is added. Right? So since we are anyway adding, so by definition or by the description of the algorithm, the cheapest edge between S and V minus S is added at every stage. And by lemma, that edge is part of every minimum spanning tree. Of G. Okay. Now, but we still need to show one thing, that this is connected. So we are adding edges, and all the edges that we are adding are part of minimum spanning tree. But what is the guarantee that we have all added all the edges to actually reach a minimum spanning tree, right? So we still need to show that T is connected. And how will we show that?
The set S is connected inductively.
Yeah. No. We are doing prims, right? Okay, yeah. The set S is connected. Wait, did I do something wrong? No, this is fine. Yeah. So the set S is connected inductively. Right, good. S is connected inductively. I mean, there are many ways to show this, but this also you can inductively, and then there are n-1 iterations. So even if it is connected inductively, I mean, you might not reach, like, you have to show that you reach everything. So when does it stop? It stops when all the vertices are included, or when n-1 iterations are there, right? So Shravan, you said this, or Manish? I forgot.
Yeah, so Shravan.
Yeah, Shravan. So I mean, just inductively it is there, but you have to.
For n iterations, yeah.
Yeah. You have to go to the ending iteration to show that all the vertices get included. So since n-1 iterations are there, there are n-1 edges, and there are no cycles by induction. So that's why it is a tree. Again, there are many ways to show that, but you need to show that. The point is that this is a thing that needs to be shown. Just showing that whatever edges are being added are part of MST is not enough. Okay. Good. Now, correctness of Kruskals, let's say.
Excuse me, sir.
Yeah.
So this is an iteration. This is an induction on what, sir?
This is an
The
induction.
iterations, or
Yeah. It is on iterations. I mean, again, you don't really need to go through induction for this. There is another more direct way that can just say that since the algorithm goes for n-1 iterations, okay, so adds n-1 edges and has no cycle by induction on the iterations. Yes, okay, fine. You have to do some induction on the iterations because you are proving the correctness of an algorithm which is iterative. And it has no cycle by induction that you can show. I mean, that is also true by the definition of the algorithm. So n-1 edges having a graph and it has no cycle, then it has to be a tree.
yeah, okay, sir.
Okay, so let's now do correctness of Kruskals. Good. So Kruskals, what we do there, we are doing like a more this thing that we just add this edge arbitrarily from somewhere to somewhere, right? So okay. So suppose at some this thing. Now again, here also similar thing will happen, that basically whatever we have this S and whatever we have this V minus S, how do we make this S and V minus S? Because in Kruskals we don't really have this S and V minus S as in the algorithm specified.
Sir, we can say that from one of the edge, from the edge we are adding, we can take the one of the S to be the connected graph till now from one of
But
the
whatever we have might not
vertex.
be connected, right?
Yeah, so even one single vertex can be said to be a connected subgraph. So like if we are adding VW,
Yes.
an edge VW, we can
Good.
take S to be the graph connected till now from V, and rest of it as a V minus S.
Good. So let's say an edge VW is being added, and then we take S to be graph spanned by, let's say spanned by all the edges, right? A set of vertices, not graph. Spanned by all the edges added till now. And now at this stage, this VW is being added. So all the, so V is also endpoint of something and so on. So this is the, so this is S, and these guys, none of the edges incident to them have been added, right? So this is how you got this S and V minus S. Okay. Now, what do we need to show? So
Sir,
first thing we need to,
but the new edge might be
yeah.
between two vertices of S only.
Oh yeah, so good. So if it is two vertices of S itself, then okay. So this is something that I did that is not correct. So we cannot do this. So fine. Let's. So the earlier thing was better actually and correct. That let S to be the connected component, vertices in the connected component, spanned by connected component containing V, spanned by the edges already added. Good. So now we want this to be connected. Whatever S is connected, and then there can be other edges which have been added, but they are on the other side, or again, yeah, they are on the other side, or they are like, they cannot be like this, by the way. Because if it was like this, we would have pulled this in S. So there are no edges like this. So remember that. That is going to be an important part in the book. Okay, so there are no edges like this. Good. So now what do we want to show? That this E that is being added right now is the minimum weight edge. Okay. So claim. So suppose there was some other edge that was minimum weight, then that will be considered, right? And that would be added. Okay. So that is by the, if there is some other edge, E prime, which is of smaller weight, then it has to be added before E. Why? Because it does not cause any cycle. And why it does not cause any cycle? Because its one endpoint will be by definition in the connected component including V, and the other endpoint will be outside this. So that is why it cannot cause any cycle to happen, right? If if V was already, if this connected component was already like this, that there were some edges that were going across, then an edge added could cause cycle. Right? But since we have taken this connected component to be in a way such that it only has the vertices which contain V, then that is why it like a connected component that contains V, only the vertices of that. That is why this cannot contain cycle, right? So, and it has not been added, or that is a contradiction. That if it had to be added, then why is why is E being added? So that is a contradiction. And then, of course, again, you need to show. So that's why E is the minimum weight edge, and by lemma, part of every MST. And that's it. Again, connectivity you can show like just like we did that. Okay, you are adding n-1 edges and so on. Connectivity is easy. Okay. Now there is another lemma that will show the reverse delete operations correctness, but I'm not going to prove that. So again, assume all edge costs distinct. Let C be any cycle. Then, and let E is equal to UV be maximum weight edge of C. Then E is not part of any minimum spanning tree. So here we are saying that if we have a cycle, look at the heaviest edge, that is not going to be part of any MST. Again, proof is similar to the line of the previous lemma, but I'm not going to do it. You can try it yourself. Again, you look at this, and see how this can be done. Okay, good. Now there is just one small thing, that how do we eliminate the assumption of edge cost being distinct? Any idea about that? Because we use that. So now suppose there are some edges which have the same cost, then how do we still find the minimum spanning tree? Because the algorithms exploited that, okay, look at the minimum cost, this cost is minimum, and so on. So what can we do in this case?
Arbitrarily choose one of them, one of the equal ones.
No, but we can arbitrarily choose, but then we need to go and change the proof of correctness and so on. And the correctness actually quite crucially relies on, for now, the way we have done it, it relies on the edge cost being distinct. So instead, we will do something else in this case. What we'll do that, okay, we want to find the minimum spanning tree. Why don't we make the edge weights non-equal, right? So perturb the edge weights. Very slightly, such that minimum spanning tree of G prime is same as, so if T is, then T is MST of G. And how can you do that? You take the edge, the weights of edges. So look at the quantity that minimizes the absolute value, let's say. Minimize E1, E2 in E, whatever cost of E1 minus cost of E2, the absolute value, and then you divide this by whatever n square or something, and then add some 1 time, 2 times to it, or remove 1 time, 2 times to it, such that what happens is that if you look at any MST of G, then you go to G prime and that remains an MST of G prime, because if you shift now any edge and if you take something else, then it is not going to be like, it is not going to be an MST, right? And now on the other hand, if you go from G prime and if you go to G, now since you have perturbed the cost very less, if G, the MST of G prime is not an MST of G, then if you take something else in G, then the difference is going to be very large, and you cannot cover up by just these perturbations. So this proof, I mean, you guys are math people, so this you can do, but the idea is just to perturb the weights very slightly so that the weights don't remain equal, and then you look for an MST in this graph.
So,
Okay, so
do we have to prove here that the order of weights have not changed? Do we have to formally prove this, or just writing this formula is enough?
Yeah, I mean, so if, yeah, you should formally prove this, that not the order of weights, actually, we are not talking about order of weights. We are saying that the MST has not changed. Okay, so this is the lemma that you will have to show is this, actually, that if T is an MST of G prime, T is an MST of G prime if and only if T is an MST of G, after doing this. Okay, so I mean, or let's say T prime is an MST of G prime, because, or this is just a set of edges. So let's say T is an MST of G prime if and only if T is an MST of G, because T is a subset of edges. So this is what you will need to show. So what is G prime now? G prime is also again actually the same. So G prime is equal to G, but just it has, like, some C prime as the cost, and G had C as the cost. So with respect to this cost, whatever is the MST is going to be the same as MST with respect to this cost. Okay, so this you can try, and basically the idea is to perturb slightly so that it does not make a difference into the overall structure. So if you find some MST there, it will correspond to an MST there. So this you can do as a homework, and tomorrow we'll look at the implementation of these two, Prims and Kruskals, and if time permits, we'll look at clustering. Otherwise, we'll get done with this greedy algorithm thing tomorrow. Okay. Any other questions about today's thing?
Excuse me, sir. I had a doubt in the assignment and not today's class.
Yeah.
Just a general query.
Okay, go ahead.
You have marked some of the questions as optional. So will you be giving bonus marks for those, or
No,
are
I mean,
they?
so I have done this bonus marks things in the past, but then, like, there are some problems with that. So it's just for your, so they are optional. You can do it for your own liking, and if you want that to be checked, we can check that, or we can discuss that. But no marks will be awarded for those questions. That is for just, for your pursual, and it's just that, we might correct them, or I can direct the TS to correct them.
Okay, sir. Thank you.
Sir, also, I have a doubt on question 1. Like, non-negative means that the functions can take.
Yeah, you have sent an email also for
Yes,
that,
sir.
right? I'll respond to that. I'll respond to that. I'll put that.
Sir, one more thing. Like, do we consider them to be like in our analysis? Do we have to also consider real numbers apart from the integers? Like, or is it just we have to check?
No. N and N0 are integers. Okay, if I didn't say that explicitly, yes, they are integers.
So, like all the comparison, we just have to do consider reals.
Yes, for integers only. So
Okay,
N is always an integer whenever we are talking about these functions.
okay.
Okay, any other questions? Okay, so thank you everyone for joining today, and see you tomorrow.